Okay, so moving on to the reading guides for 7-7. Before we begin, though, just a reminder of what we're looking at here. Exponential growth, exponential decay. Please notice how similar these two are. The difference being this B part here, right? This B is 1 plus the percentage of change of growth. The B here on decay is 1 minus the percentage of change of growth, again expressed as a decimal. And here, A initial is the initial amount, here A initial amount. And the exponent's in the same place. The same formula, very different results here. Notice this B here is going to be greater than 1. This B is going to be less than 1. Between 0 and 1, right? 1 and bigger. So bigger than 1, growth. Smaller than 1, decay. Exactly 1, nothing. And we'll also talk about compound interest. And this one's kind of a big formula. You notice the N is used twice. Please, you got to know what the different parts mean. And I do mean that, people. Please memorize this. So A is the balance. P is the principal, the initial amount you start with. R is the annual rate expressed as a decimal. Annual rate, that's the yearly rate. N is the number of times of year, like quarterly or annually is only 1, right? And T is the time in years. Now the thing is, I can expect you to find any one of these things that I'm looking for if I give you certain bits of information. So modeling exponential growth, nice example here. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. If the trend continues, how much will you spend at restaurants in 2015? So in that 10 years worth of growth. Notice you could also use this one if you wanted to go back in time. Like, okay, what was it 10 years before that, right? Okay, so X is the number of years since 2005, so 10 years. Y is the annual amount spent in restaurants in billions of dollars. A is the initial amount, that's the $360 billion. B is the growth factor, notice 7%. Express the decimal, 0.07, add them together for growth, 1.07. So plug everything in, Y is 360 times 1.07 times X. So you got to know these parts, the plus and the minus parts, and then what to do with them. I'm going to plug the 10 in here for X, by the way, because it's 10 years, right? 2015 to 2005. And then plug the numbers, and you get about $708 billion will be spent in 2015. So the same thing, I go say, okay, let's go back to 1995, and you put a negative 10 here. So that's the kind of thing we're looking at here. Okay, so now for a fun one. Suppose the population of a town was 25,000 people in 2000. If the population grows about 1.5% each year, what will the approximate population in 2025? So before we start, so we know for sure it's going to be a 25-year span, right? So we have that whole 25 years. Got to put that down. Population started as 25,000. We need this also. 1.5 is a decimal, so 0.015. So our formula. Y equals A, which is 25,000, that's the initial amount, times 1 plus the growth factor, this one right here, to 0.0, or the percent rather, 0.015 to the x power. So that looks like Y equals 25,000 times 1.015. There's a 1 in there, I promise, hang on. Right there, 1.015. All that to the x power. In this case, our x is going to be 25. So Y equals 25,000 times 1.015 to the 25th power, because it's 25 years. Y equals 25,000 times 1.451. Which, again, this is rounded, by the way. You use your calculator, and it goes on forever, obviously. So that's going to give us about 36,274 people. It's like 36273.6 or something like that. So we don't have 0.6 people because, that's gross. So 36,274. Don't forget the label people. Okay, so problem number 2, or example number 2, I should say. That's not what I wanted. There we go. Suppose that when a friend was born, we've seen this problem, right? Your friend's parents deposited $2,000 in an account paying 4.5% interest compounded quarterly. Will the account balance be after 18 years? So we know, according to our formula, that, right here, principal, 2,000, 4.5% interest, compounded quarterly, that's 4 times a year. 18 years is what I need to shoot for. So, what I'm going to end up with, the amount of money I'm going to get. P principal is 2,000. 1 plus, and again, so the 4.5% as a decimal is 0.045 over n, that's 4 times a year, raised to the n, 4 times a year, times 18 years. 4 times 18, 0.045 divided by 4, add the 1, and raise this to the 72nd power, then multiply by 2,000, again about $4,475.53 after 18 years. We'll do your got it 2 on the next page. So to kind of help us model that, use that last one as a model, we did use the same problem, only this time we're going to compound interest monthly for the same 18-year period. So we start out, we know that we have $2,000 in there, so A equals $2,000 times 1 plus that 4.5%, so 0.045 over 12 times, so it's monthly, it's 12 times a year, right? And that 12 times a month, or times a year rather, times 18 years still. So A equals 2,000 times 1 plus 0.045 over 12 raised to the 216th power. A equals 2,000 times, and inside here I'm going to go ahead and calculate that. So you're going to take that 0.04, oops, sorry, wrong one here. There we go, 0.045 divided by 12, and then add the 1 on, which is going to be, let me get back to my marker here, it's going to be 1.00375, all raised to the 216th power. Order of operations, we're going to take this number to the 216th power, so it's A equals 2,000 times about 2.2445, and that's going to yield about $4,489.01, which is a little different. I think you had 4,475. So you gain like $14 by picking a bank that gave you monthly compounding of interest, right? So it's like what, not even $1 a year over the entire 18 years is the difference it made. But with a larger amount of money, maybe more might be important to you. So moving on to decay, again, a lot like growth, except that B, that base, right, is going to be 1 minus the percent of growth, or percent of decay. I do apologize, not growth, since it's a decay model. Same formula, though. The kilopascal, again, we talked about that unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter that you go up, right, in altitude, the pressure decreases about 11.5%. What is the approximate pressure at an altitude of 3,000 meters? So we've got, again, X is the altitude, right, in thousands of meters. Y is the atmospheric pressure in kilopascals. A is the initial pressure that we start with. That's at sea level, the 101 kilopascals. And B is the decay factor, which is 1 minus 0.115, because again it's 11.5% expressed as a decimal, and it's minus because it's decay. Trying to help you out, make sure you catch every part of this. So there's our formula, right? Plug everything in. We use the equation to estimate an altitude of 3,000 meters. So we plug our 3 in for X and calculate and get about 70. So 8.885 to the third power times 101 is about 70 kilopascals at 3,000 meters of height. So again, playing off the last problem, the only thing we would like to change this time says, what is the atmospheric pressure at an altitude of 5,000 meters? So you'd throw a 5 in there, right? So we're going to have that Y equals that 101 times 885 raised to the 5th power, which is about 101 times 0.5, because it's a decimal here, 0.54289, I think it goes on forever, right? Multiply that out, Y is 54.83, which really we're looking at approximately 55 kilopascals. So again, where do the numbers come from? Let's make sure we understand that part. This 101 is the pressure at sea level. Here, 0.885 is 1 minus that percent of that 11.5% expressed as decimal, so 1 minus that. And up here is the number of meters in thousands of meters. Now, Part B, why do you subtract the percent decrease from 1 to find the decay factor? Here, again, because the decimal equivalent of 100% is 1. So that's why you turn this into a decimal, and then subtract. So you turn that 11.5 into a decimal. Otherwise, it'd be 100% minus that, and then still convert to a decimal in the end anyway. So it's still going to get you there.